Even today's most technologically advanced militaries would usually prefer to fight in clear weather and blue skies. But as war-fighting technologies proliferate, the side with the technological advantage will prefer to fight in weather that gives them an edge. The U.S. Army has already alluded to this approach in their concept of owning the weather. Accordingly, storm modification will become more valuable over time. The importance of precipitation modification is also likely to increase as usable water sources become more scarce in volatile parts of the world. As more countries pursue, develop, and exploit increasing types and degrees of weather modification technologies, we must be able to detect their efforts and counter their activities when necessary. As depicted, the technologies and capabilities associated with such a counter-weather role will become increasingly important. The importance of space weather modification will grow with time. Its rise will be more rapid at first as the technologies it can best support or negate proliferate at their fastest rates. Later, as those technologies mature or become obsolete, the importance of space weather modification will continue to rise, but not as rapidly. To achieve the core capabilities, the necessary technologies and systems might be developed according to the process depicted in Figure 5.2. This figure illustrates the system's development timing and sequence necessary to realize a weather modification capability for the battle space by 2025. The horizontal axis represents time. The vertical axis indicates the degree to which a given technology will be applied toward weather modification. As the primary users, the military will be the main developer for the technologies designated with an asterisk. The civil sector will be the main source for the remaining technologies. Conclusions. The world's finite resources and continued needs will drive the desire to protect people and property and more efficiently use our croplands, forests, and rangelands. The ability to modify the weather may be desirable, both for economic and defense reasons. The global weather system has been described as a series of spheres or bubbles. Pushing down on one causes another to pop up. We need to know when another power pushes on a sphere in their region, and how that will affect either our own territory or areas of economic and political interest to the U.S. Efforts are already underway to create more comprehensive weather models, primarily to improve forecasts, but researchers are also trying to influence the results of these models by adding small amounts of energy at just the right time and space. These programs are extremely limited at the moment and are not yet validated, but there is great potential to improve them in the next 30 years. The lessons of history indicate a real weather modification capability will eventually exist despite the risk. The drive exists. People have always wanted to control the weather, and their desire will compel them to collectively and continuously pursue their goal. The motivation exists. The potential benefits and power are extremely lucrative and alluring for those who have the resources to develop it. This combination of drive, motivation, and resources will eventually produce the technology. History also teaches that we cannot afford to be without a weather modification capability once the technology is developed and used by others. Even if we have no intention of using it, others will. To call upon the atomic weapon analogy again, we need to be able to deter or counter their capability with our own. Therefore, the weather and intelligence communities must keep abreast of the actions of others. As the preceding chapters have shown, weather modification is a force multiplier with tremendous power that could be exploited across the full spectrum of war-fighting environments. From enhancing friendly operations or disrupting those of the enemy by a small-scale tailoring of natural weather patterns to complete dominance of global communications and counter-space control, weather modification offers the warfighter a wide range of possible options to defeat or coerce an adversary. But, while offensive weather modification efforts would certainly be undertaken by U.S. forces with great caution and trepidation, it is clear that we cannot afford to allow an adversary to obtain an exclusive weather modification capability. Why is the ionosphere important? The ionosphere is the part of the Earth's atmosphere beginning at an altitude of about 30 miles and extending outward 1,200 miles or more. This region consists of layers of free electrically charged particles that transmit, refract, and reflect radio waves, allowing those waves to be transmitted great distances around the Earth. The interaction of the ionosphere on impinging electromagnetic radiation depends on the properties of the ionospheric layer, the geometry of transmission, and the frequency of the radiation. For any given signal path through the atmosphere, a range of workable frequency bands exists. This range, between the maximum usable frequency, MUF, and the lowest usable frequency, LUF, is where radio waves are reflected and refracted by the ionosphere much as a partial mirror may reflect or refract visible light. The reflective and refractive properties of the ionosphere provide a means to transmit radio signals beyond direct, line-of-sight transmission between the transmitter and receiver. Ionospheric reflection and refraction has therefore been used almost exclusively for long-range HF, from 3 to 30 MHz communications. Radio waves with frequencies ranging from above 30 MHz to 300 GHz are usually used for communications requiring line-of-sight transmissions, such as satellite communications. At these higher frequencies, radio waves propagate through the ionosphere with only a small fraction of the wave scattering back in a pattern analogous to a sky wave. Communicators receive significant benefit from using these frequencies since they provide considerably greater bandwidths and thus have greater data carrying capacity. They are also less prone to natural interference, noise. Although the ionosphere acts as a natural mirror for HF radio waves, it is in a constant state of flux, and thus its mirror property can be limited at times. Like terrestrial weather, ionospheric properties change from year to year, from day to day, and even from hour to hour. This ionospheric variability, called space weather, can cause unreliability in ground and space-based communications that depend on ionospheric reflection or transmission. Space weather variability affects how the ionosphere attenuates, absorbs, reflects, refracts, and changes the propagation, phase, and amplitude characteristics of radio waves. These weather-dependent changes may arise from certain space weather conditions such as 1. Variability of solar radiation entering the upper atmosphere. 2. The solar plasma entering the Earth's magnetic field. 3. The gravitational atmospheric tides produced by the Sun and Moon. And 4. The vertical swelling of the atmosphere due to daytime heating of the Sun. Space weather is also significantly affected by solar flare activity, the tilt of the Earth's geomagnetic field, and abrupt ionospheric changes resulting from events such as geomagnetic storms. Lee's summary: the ionosphere's inherent reflectivity is a natural gift that humans have used to create long-range communications connecting distant points on the globe. However, natural variability in the ionosphere reduces the reliability of our communication systems that depend on ionospheric reflection and refraction, primarily HF. For the most part, higher frequency communications such as UHF, SHF, and EHF bands are transmitted through the ionosphere without distortion. However, these bands are also subject to degradation caused by ionospheric scintillation, a phenomenon induced by abrupt variations in electron density along the signal path, resulting in signal fade caused by rapid signal path variations and defocusing of the signal's amplitude and/or phase. Understanding and predicting ionospheric variability and its influence on the transmission and reflection of electromagnetic radiation has been a much-studied field of scientific inquiry. Improving our ability to observe, model, and forecast space weather will substantially improve our communication systems, both ground and space-based. Considerable work is being conducted, both within the DoD and the commercial sector, on improving observation, modeling, and forecasting of space weather. While considerable technical challenges remain, we assume for the purposes of this study that dramatic improvements will occur in these areas over the next several decades. Research to better understand and predict ionospheric effects. According to a Spacecast 2020 study titled Space Weather Support for Communications, the major factors limiting our ability to observe and accurately forecast space weather are: 1. Current ionospheric sensing capability. 2. Density and frequency of ionospheric observations. 3. Sophistication and accuracy of ionospheric models. And 4. Current scientific understanding of the physics of ionosphere-thermosphere magnetosphere coupling mechanisms. The report recommends that improvements be realized in our ability to measure the ionosphere vertically and spatially. To this end, an architecture for ionospheric mapping was proposed. Such a system would consist of ionospheric sounders and other sensing devices installed on duty and commercial satellite constellations, taking advantage in particular of the proposed Iridium system and replenishment of the GPS and an expanded ground-based network of ionospheric vertical sounders in the U.S. and other nations. Understanding and predicting ionospheric scintillation would also require launching of an equatorial remote sensing satellite in addition to the currently planned or deployed DoD and commercial constellations. The payoff of such a system is an improvement in ionospheric forecasting accuracy from the current range of 40 to 60% to an anticipated 80 to 100% accuracy. Daily worldwide ionospheric mapping would provide the data required to accurately forecast diurnal, worldwide terrestrial propagation characteristics of electromagnetic energy from 300 MHz. This improved forecasting would assist satellite operators and users, resulting in enhanced operational efficiency of space systems. It would also provide an order of magnitude improvement in locating the sources of tactical radio communications, allowing for location and tracking of enemy and friendly platforms. Improved capability to forecast ionospheric scintillation would provide a means to improve communications reliability by the use of alternate ray paths or relay to undisturbed regions. It would also enable operational users to ascertain whether outages were due to naturally occurring ionospheric variability as opposed to enemy action or hardware problems. These advances in ionospheric observation, modeling, and prediction would enhance the reliability and robustness of our military communications network in addition to their significant benefits for our existing communications network. Such advances are also requisite to further exploitation of the ionosphere by active modification.